Let's look at example number 11, which is a little bit harder, but very similar probability question. It says in Yahtzee, 5 6-sided dice are rolled. How many outcomes are possible? Determine the probability that all dice are at least fives. So if you've ever played Yahtzee, you get all the dice, you shake them up and you roll them, and then there's various different goals. And if we want to find the probability of certain events, fairly easy to do. But again, easy. What I mean is like there's a way of going through it, and if you're following through each of these steps, it can be helpful in determining those particular things. But it's always helpful to begin with what is the size of my sample space? Like how many outcomes are possible? But again, if I think about each die could be 1 through 6. So there's 6 options. And since I'm rolling 5 6-sided die, the number of outcomes, go ahead and note this over here, outcomes, again, I could think about it, well, it's 6 times 6 times 6 times 6 times 6. Uh, which is because each die could be 1 through 6. There's no replacement, right? It's not really a permutation question, um, because there is like each die is a unique object. But basically, it's going to be 6 to the fifth power for the number of outcomes by fundamental counting principle. So 6 to the fifth is quite a bit of outcomes, but there are 776 unique Yahtzee outcomes, which is pretty interesting. But also notice that that doesn't take into account the duplicate. Like for example, is 55655 the same as 5556? Sorry, 55565 or 65555, which technically yes, based on the rules of the game. But when you're thinking about probability, it's more helpful to think about them all as unique outcomes. Like with heads, tails is different than tails, heads, just because. So basically, whether or not the duplicate nature really matters to the problem, because again, you could be thinking about the difference. Well, are these 4 different outcomes really different? Technically, yes, because when I'm thinking about a series of outcomes, they are different possibilities in the grand scheme of things. So hopefully that isn't making it more confusing. Because like if I think about order doesn't really matter when I'm flipping coins or or when I'm rolling dice. But it helps with probability to consider each as a unique outcome due to the nature of the complexity of what could happen. And obviously we're not going to write out the sample space because we'd have 7,776 objects. But basically, like here, I wrote out the whole sample space. But really, what's more important is to know what's the size of the sample space. So basically, I could write that is hashtag S, the number of objects, total Yahtzee hands. And also, if I want to figure out the second part of the question, determine the probability that all are at least fives, what I could do, there is a mathematical formula for finding that, which is pretty simple, but how would you come up with it? How do you know to do it? Well, let's just, another way you could do it, which is probably how I would do it if I wasn't sure, is just figure out what's the event space. So how many possibilities in this vast series of things could be at least 5. And that's pretty easy to do because it's a lot smaller, right? Well, of course, if all were sixes, if I rolled 5 6s, I wrote too many because we roll 5 dice, plural, in Yahtzee, then that's one outcome. Or if they were all fives, that's fine. Or a combination of sixes and fives, which it could be any number of each of these. So really, this is 5 choose. What this will end up being was 5 choose 0 plus 5 choose 1 plus 5 choose 2 plus 5 choose 3, etc., all put together. And there's kind of an interesting number that comes through all of that if we finish it. But anyways, so we could have 1 5 and the rest sixes, which that 5 could go anywhere. And again, when developing my sample space, it is pretty elaborate. And, I wouldn't really necessarily know how many there would be before I started the question, but quite clearly when I'm working on it at this point, I'm thinking, okay, this is a pretty elaborate question. And there's got to be a simpler way. But, if you don't know the simpler way, you got to still figure it out. So you might as well just continue. And so those are all the possibilities of having 1, 5 in the same way. And I notice that if I do all that, that would be 5 ways of doing it. And then again, the math here is 5 choose 5, 5 choose 0, 5 choose 1. And basically, if I add up all of those, that's going to be the sum of the number of events in this particular case. But let's go ahead and just finish. So I could have, in the same exact way, a single 6 and the rest 5s. So that would be 6, 5, 5, 5, 5, 5, 6, 5, 5, 5, 5. Another reason that I suggest you probably don't do it this way is because it's really easy to leave off some of the possibilities. I've kind of trained my brain to be able to think about them all. And as I say that, I'm probably going to miss them and be eating my words here in a second. But like dealing with permutations and vast numbers of different arrangements can be but quite difficult. But I try to focus on a very methodical way of going through each of those things. So that would be 5 choose 4, which is of course also 5 for that many. And then if I'm moving on to what if I have 2 5s or 3 5s, that would be 5 choose 3 and 5 choose 4. And I could write them all out. And if you recall that 5 choose 4 and 5 choose 3 and 5 choose 2 are both 10, but then there will be, I'm actually going to, well, let's just write them all out just for the sake of attrition. But basically there should be 10 ways to pick 2 6s and 3 5s and vice versa. So let's go ahead and just find them all. But notice that the combination math and Pascal's triangle can kind of help with doing all this. Anyways, if you can see, I'm hesitating because I really don't want to, because I'm getting to the point where this question is becoming tedious for me, but we're going to do it. Okay, so I could have 5, 5, 6, 6, 6, 5, 6, 5, 6, 6. And again, I'm looking for 10 results here with 2 5s. I could have 5, 6, 6, 5, 6, 6. Whoops, that's too many 6s. 5, 6, 6, 6, 5. Interesting how 666 and 777 keep showing up in this example. We'll pretend that there's nothing sinister going on, though. Sorry, lame jokes are really bad today, I guess. And then we could have 6, 5, 6, 6, 5, or 6, 5, 6, 5, 6, 6, 5, 5, 6, 6. I don't know if you can see the logic that I'm following here, but I'm just trying to, I'm kind of thinking about a string of 6s and putting 2 5s in those particular positions. And, I'm starting off with them really early and then sort of moving the second 5 as far as I can. Then, so there were 4 ways to start with 5. Then there's 3 ways to start with 6, 5. And so on. I'm progressing through these till I get the rest of them. And then there could be 6, 6, 5, 6, 5, or 6, 6, 5, 5, 6, or finally 6, 6, 6, 5, 5. So those are and that should amount to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I know that those are all the arrangements of having 2 5s and 3 6s. And similarly because 6s and 5s are arbitrary, I could interchange them here. There would be 10 more ways to do 2 6s and 3 5s. And I'll follow the exact same pattern. I could do 6, 6, 5, 5, 5. I could do 6, 5, 6, 5, 5. 6, 5, 5, 6, 5. 6, 5, 5, 5, 6. 5, 6, 5, 5, 6. And again, you can see why I wouldn't recommend that you solve the problem this way, but through exhaustion, you could eventually figure this out. 5, 6, 6, 5, 5, 5, 5, 6, 5, 6, and two more, 5, 5, 6, 6, 5, and 5, 5, 5, 6, 6. But anyways, that amounts to the sum of all of those combinations added up divided by 2 or 5 to the 6th power. So if I do just add all those up, well, that was just 10 plus 10 plus 5 plus 5 plus 1 plus 1. That would be 32 outcomes, which a number that is quite simple, which is um, not not exactly coincidentally 32. But again, if you add up the line of Pascal's triangle, right, which was the 6th line, because the first line would be 0 combinations, which is kind of silly, but it was just one. Again, I've erased my Pascal's triangle already. Actually, no, I think it's in the previous page of notes. Yeah. But if I were to add up all of those lines, that would be a much simpler way of figuring out the number of outcomes with at least 5s on them. And if you wanted to know, well, what about having at least 4s? Well, then again, you'd have to think it through as well. But my point is there's a way to think it through and a way to simplify these calculations quite a bit. But anyways, what I wind up with finally is that the probability of getting all at least 5s on all the dice would be, well, since it's an equal probable space, because again, a dice, assuming it's equally likely to roll 1, 2, 3, 4, 5, or 6, we had 32 outcomes divided by 7,776 possibilities. My dog is barking. Sorry, hopefully you can't hear him too well. But that would give us a probability of approximately 0.004115, which is about 4.12%. Sorry, messed that up. Oops, it is 0.412% chance. So less than 1%, or basically very, very unlikely, less than 1 in 100. Approximately 1 in 200. And like odds are a different way of explaining a probability, which can be confusing too. But actually, odds are technically not what I just stated. 1 to 2 as opposed to 1 in 2. It doesn't mean the same thing. Which, if you look in the book, it defines odds. We're not going to bother with that in this class. But anyways, that gives us one method of solving such a question.